Hello and welcome to Lecture 7 for the course ECE 1B Freshman Seminar. This lecture is scheduled for Monday, May 11th, 2020. And your attendance report for this lecture is due on Wednesday, May 13th, 2020 by 6:30 p.m. Okay, the title of the lecture is Task Scheduling. Now, the puzzles that lead us to the notions of task scheduling are Sudoku puzzles. A particular version of Sudoku is well known, and you have likely seen them in various newspapers and magazines, including our campus newspaper, Daily Nexus. But there are many variations, and I'll show you some of those variations in the course of today's lecture. So the first variation that we'll consider is what is known as mini Sudoku. It's a 6x6 grid. Standard Sudoku, the one that most people are used to, is a 9x9 grid. And the objective of solving a Sudoku puzzle is to make sure that different numbers, so in the 6x6 puzzle, numbers 1 through 6 are used in the various boxes, and boxes or cells in the same row should contain different numbers, 1 through 6. Cells in each column should contain numbers 1 through 6. And those 2x3 boxes also should contain different numbers 1 through 6. So the objective of the puzzle is, given some initial configuration with some of the numbers shown, you have to fill the remaining cells so that the constraints that I just told you about are satisfied. In other words, the first row must contain numbers 1 through 6, and the number 2 is already written in one of the cells. So you have to put the numbers 1, 3, 4, 5, and 6 in the remaining cells, while also taking care that this box over here also contains the number 1 through 6. Okay, so I mentioned you have to put 1 in some order, the numbers 1, 3, 4, 5, 6, but 4 cannot go in either of these two boxes because this box already contains a full 4. So 4 must be on this side. Okay? And if you're interested in playing mini Sudoku puzzles, several magazines and newspapers carry them. And there's also this website where you can get many Sudoku puzzles to solve online. So in this puzzle, as you see, the number 2 appears in this cell at the top. And within that column, you cannot have any other cell that contains 2. Okay? So for example, if you look at this box, at this 2x3 box, it is missing the number 2. But the number 2 cannot occur in this column. Therefore, the only position for the number 2 is this one. Okay, so Sudoku is sometimes characterized as a mathematical puzzle. It's really not a mathematical puzzle, but it's a logical puzzle. Because even though superficially it looks like you're doing math because there are numbers involved, You can actually do Sudoku with letters, so that no numbers involved at all. So in this version, you have to put the letters A through F in the boxes so that each row contains all the letters A through F. Each column contains all the letters A through F. And each of these boxes, each of these 2 by 3 boxes, contains all the letters A through F. Okay, so this is just to emphasize that it's not really a mathematical puzzle. So what I can do is I can observe that this cell at the top right must contain C. And the reason for that is that this box needs a C. It doesn't have a C yet. A C cannot go in this column because it already has a C. And a C cannot go in this column because it already has a C here. So the only place, the only option open for putting C is there. So these are sort of freebies. When you solve Sudoku puzzles, sometimes you can, the choice for a particular cell is forced, and therefore it's easy to make progress. Here's another place where you should put C. Okay, why does C go there? Because this box needs a C. The C cannot go in this part of the box because there is a C in that row. It cannot go in this column because there's a C there, so that's the only choice that is left. Okay, I leave it up to you to argue that another C can be placed there. The letter A should go there because, again, this box needs an A. A cannot go into these 2 cells, and it cannot go into this cell. Therefore, that's the only option for it. So similarly, these freebies make it easy. So I already made a lot of progress without having to worry about, choices. There are no choices in these boxes. When there are choices, it becomes a little bit more difficult. Okay, so for example, I notice in this leftmost column, I need the letters A and E. A and E are missing because B, C, D, and F are already there. So A or E can go into this box. I don't know which one because neither one of the choices conflicts with what I already have in this row or in this box. A or E can go here. So this is when I solve a Sudoku puzzle and I'm using a pencil, I sort of pencil in A, E there and A here. Maybe later I can decide whether A goes up there and E down here or just the opposite. And then I erase those and just put the final choice there. Many online Sudoku puzzles have this notation capability where you can put multiple choices so that you remember, what options are available in each box. Okay, so you can basically continue in this manner, and eventually this ambiguity will be resolved once you make other choices in the puzzle. Okay, this is an example. So Sudoku puzzles, the 9 by 9 standard variety, come with different levels of difficulty, from very easy to extremely hard. And generally speaking, although this is not a rule, the easy puzzles have more entries specified at the outset. That's sort of a clue or a sign that the puzzle is easy. If you have fewer entries, fewer cells already filled in, that tends to be harder, although there isn't a sure correspondence between the number of entries and the difficulty. The simpler puzzles, basically, you can make progress through those forced selections, so that before you know it, many of the cells are already been filled up and you're left with only a small number of choices at the end. So let's try to solve this puzzle, or at least partially. Okay, so strategy 1 for solving Sudoku is identifying a missing number from a row, column, or block. And if you can exclude all but one cell for that number, then write it down. So for example, in this box, I need an 8. There's no 8. This column already has an 8. This column already has an 8. So 8 must go into this column, and there's just one option for that. So these are the freebies that I was talking about before. There are quite a few of them, and this easy puzzles tend to have a lot of these freebies. So as I said, you can make a lot of progress without much thinking. Okay. I went too far. Okay, now you see that in this rightmost column, numbers 1, 2, 3, 4, 5, and 6 appear. So 7, 8, 9 are missing. So those 3 blank cells should contain 7, 8, and 9. Okay, so excuse me. Okay, so each of these 3 boxes, if you want, you can make a notation 7, 8, or 9 in all 3 of them. But right here, you see the choices here are 7, 8, 9, but 7 and 8 are not really choices, because that row already contains 7 and 8. So 9 is really the only choice for that cell. Okay, so I need 7 and 8 now for the remaining 2 cells in that column. 7 or 8 here, 7 or 8 here. But again, here, 8 is not really an option, so it has to be 7. And then 8 will go there, okay? So basically, you look for columns or rows that are more or less filled up. There are only a few blank entries. And then decide what is missing from that column, and then see if you can make progress. If you can't make progress, you just write both remaining options, 7 or 8 here, 7 or 8 here, and leave it to be resolved later on. Okay, now I can see that 7 should be put there. And the reason for that is that this row already contains a 7. This row already contains a 7. And this column already contains a 7. So the only place for 7 is there. Okay, so at some point I can no longer make progress with these forced entries. Then I have to do something else. So for example, you see from this row 2 and 5 are missing, but 2 or 5 can go here, go here. Neither one is in conflict with anything else. So I can't decide at this point. Similarly, 5 and 8 are missing from this middle row. So I write 5, 8 here. Neither 5 nor 8 is inconsistent with anything that appears there. 5, 8 here. So I leave this for later resolution. This is just a notation to remember that the only 2 options there are 5 and 8. Okay, so I can't make a decision there yet. All right, there are situations, however, when there are such ambiguities, I can use logical reasoning to resolve the ambiguity. And basically, that's how I make further progress. So let's say in this row, I notice that 1, 2, 3, and 4 are missing. Okay, 1, 2, 3, and 4. For these two boxes, 1 and 4, these two cells, 1 and 4 are already inside this box. So of those 4, only 2 or 3 can go in each of these boxes. So 1, 2, 3, 4 is what's missing from this row, but 1 and 4 are already in this box, so 2 or 3. Okay, now 2 is here, so just 1, 3, 4 are options here. 3 is here, so 1 or 4 are the options there, and 4 is in this column, so 1 or 3. So you notice that there is still ambiguity in the sense that each of those cells has two choices, okay? However, the nature of this ambiguity here is that I can resolve it by the following argument. I say this cell here will have 2 or 3. This cell here, so if this one has 2, this one will have 3. If this one has 3, this one will have 2. So 2 and 3 will appear in those two cells one way or the other. Therefore, 3 cannot occur here. Therefore, that cell should be 1. And once 1 is chosen for that cell, 1 cannot occur there. So you notice that even though there were two choices for each box, by using this reasoning that 2 and 3 will be taken by these two cells, and therefore they cannot occur anywhere else, I was able to resolve that problem. But of course, I can't resolve this part of the ambiguity yet. All right, so you get the hang of it. You basically argue, and then whenever you can't make a decision, just write down the choices that are available for each box, with the hopes that later, you can use information from multiple cells to make a decision. So this is an example of a hard Sudoku puzzle. I won't say anything more about this one. This is just for you to, if you are interested in the puzzle, get some exercise solving a harder version of the puzzle. Hard puzzles typically have fewer entries. Also, they have fewer of those freebies. In other words, you can typically at the very beginning fill a few cells easily, but then those cells dry up rather quickly, and then you have to use more logical reasoning to make progress. So how does one construct these Sudoku puzzles? Well, you can go backwards, okay? Basically, start with a filled out grid that satisfies the constraints. In other words, numbers 1 through 6 appear in each row. Numbers 1 through 6 appear in each column. And then numbers 1 through 6 appear in each of these 2 by 3 grids. And then try to remove entries in such a way that those entries can be restored uniquely. Now, not every Sudoku puzzle has a unique answer, but Sudoku puzzles used in newspapers and magazines always have unique answers. The reason is that these newspapers and magazines want to be able to give you the solution maybe the next day or the next week. So the solution, there should be one solution. If there are 20 different solutions to the puzzle, then they can't easily provide all those solutions. So all puzzles that you see, either in newspapers or magazines or books that contain collections of Sudoku puzzles, have unique answers, because then you can look up the answer to see, if you get stuck and can't solve it, you can look up the answer. So you go backwards. So for example, I can remove this 2 because once that 2 is removed, the only option for that box is 2. Okay, because this row is missing a 2, and therefore I can restore it. Okay, so you remove numbers from cells if you know that you can restore that number by just arguing based on the remaining numbers. So basically, if a row is complete, you can remove any of the numbers. If a column is complete, if a box. So for example, I have a complete box, 2 by 3 box there. I can remove one of the numbers. Let's say that 5. And I know that I can put 5 back there. Okay, so I can continue in this way, remove that 4, remove that 3 by sort of making sure that whatever I remove can be restored unambiguously, uniquely. Okay? So question 1 for this lecture is for you to remove additional entries from this puzzle. So start from this state that you see there and see what you can remove. So for example, can you remove this 3? The answer is yes, because this box needs a 3, but the 3 cannot go here and it cannot go here. So that's the only position that is possible for it. Therefore, if I remove it, going backwards and solving it, I would put 3 there, and therefore I will get the same puzzle that I started with. So your first assignment, question 1, is remove additional entries from this puzzle and making sure that you maintain the uniqueness of the solution. Question 2 is also on this same slide. I'm asking you to build a 4 by 4 Sudoku puzzle with a unique solution and the fewest initial entry. So a 4 by 4 Sudoku puzzle has a 4 by 4 grid and 2 by 2 regions. Okay, so there are 4 rows, 4 columns, and 4 2 by 2 boxes. Okay, so the numbers 1 through 4 will be placed in the cells to solve it. And I'm asking you to make a Sudoku puzzle 4 by 4 with a unique solution and the fewest initial entry. So there are 16 numbers in a 4 by 4 Sudoku puzzle. Try to minimize the number of entries that you provide at the outset while ensuring unique solution. So for example, can you do it with 6? Can you do it with 5? So see what is the smallest number of entries that you can place in the 4 by 4 puzzle and have it maintain a unique solution. Okay, now Sudoku, there are some interesting facts about it. The number of different solutions that you can make for a 9 by 9 puzzle is this huge number shown here. Okay, 1, 2, 3, 4, 5, 6, 7 group of 3 digits. So that's 21, 22 digits in this number. Okay, so that's a huge number. That's the number of possible solution grids. So there's basically an endless supply of Sudoku puzzles. It's very unlikely that you will ever see the same puzzle in the course of doing daily puzzles. And this number, interestingly, is equal to the product of these 4 numbers: 9 factorial, 72 squared, 2 to the power 7, and this number 27,704,267,971, which happens to be a prime number. So it's mind-boggling that this number, the number of possible grids, 9 by 9 grids for Sudoku, somehow related to this large prime number. Okay, it's not any less interesting and amazing that 72 square and 9 factorial and to the 7 occur here. In a 9 by 9 Sudoku puzzle, you may need at least 17 initial entries or clues for the solution to be unique. But nobody is sure of this fact. In other words, some people guess that maybe 16 clues would be sufficient in some cases, but no one has either an example of that or a counterexample. Okay, so nobody knows whether 16 clues would be sufficient, but we know that there are Sudoku puzzles with 17 starting clues and unique solutions. Okay, as I said, there are many, many variations of Sudoku. Here is one variation in which we still need to have different numbers 1 through 9 in rows and columns, but the regions in which unique numbers should be preserved are not squares, 3 by 3 squares as we had before, but they're irregularly shaped areas with 9 cells. Okay, so basically what this means is that within this area, this irregular, this is sort of like a jigsaw puzzle. Within this area, I have to have numbers 1 through 9 without repetition. Okay, so I don't have 1 in that area. I have 2. I don't have 3, 4, 5, 6, 7, 8. So 1, 3, and 9 should go into these 3 cells, 1, 3, and 9. Now this one cannot be 3 because that column already contains 3. So if I want to write in pencil, I can write 1, 9 here. Those are the only options. So 1, 3, 9 here. Again, 9 is not possible. So 1 or 3 would be the options there. And all 3 possibilities, 1, 3, 9, can go there. So 1, 3, 9, 1, 3, 1, 9. I can't decide at this point, but I can make that notation on the puzzle in case I can resolve the ambiguity later on. Okay, so question 3 is for you to solve this irregular Sudoku puzzle. It's a challenge because it's unlikely that you have seen this before. Here are a whole bunch of other variations. If you're interested to read about, what these are and how you solve them, on this slide, the PowerPoint file contains a notes section at the bottom. So the notes associated with this slide actually describe how these games are played. Some of them are easier to describe. For example, here the less than and greater than signs have their normal meaning, and basically you're restricted to put a number that is smaller on this side and larger. So for example, you can put 1 here and 6 here, okay, but not 3 here and 2 here. Okay, so you have to honor those less than or greater than relationships for all the boxes. Okay, let me just describe one more of these, and the others, if you are interested, you can read on your own. Maybe 2 more. This one, basically you're given clues not as numbers that are in there, but as choices. So for example, here you see 2, 6, 6, 7, meaning that these 4 boxes around that point will have the numbers 2, 6, 6, 7, but we don't know in what order. Of course, the 2 6s must be diagonal, so the 2 6s must go here, or they must go here, because they can't be in the same row or in the same column. Okay. can't read some of these. This may be 3789, meaning that these 4 cells contain 378. And this one is also interesting, the lower left puzzle. These thermometers, the numbers should be in increasing order. So for example, this thermometer can have maybe 2, 3, 4, 5, 6. They don't have to be consecutive. 2, 3, 6, 7, 8. But of course, 3 cannot go here because there's only a 3 in that box. So the smallest number that can start here is 2, but 2 is also impossible because of this 2. 3 is impossible. So the smallest number is 4 on that thermometer. 4, 5, 6, 7, 8. Okay, so there is some room for playing with it. So instead of 4, 5, 6, 7, 8, could be 4, 6, 7, 8, 9. But that's not possible. This cannot be 9 because this row already contains 9. So it must be 4, 5, 6, 7, 8. That's the only way you can put increasing numbers on that thermometer. Okay, so it's interesting. So these are just some of the variations that you can find for Sudoku puzzles. There are many more. Here are some other examples. So you can have 6 by 6 Sudoku. We already talked about it. Mini Sudoku with 2 by 3 blocks. You can have 16 by 16 with 4 by 4 blocks. And those are usually more time consuming because you have, it's like, you know, the huge Sunday crossword puzzles where there are many clues and you have to spend sometimes hours solving it. So 16 by 16 Sudoku is not necessarily harder, but it's just more work. And this one is a combination of Sudoku with Rubik's Cube. So you have to turn the faces of this cube so that distinct numbers 1 through 9 appear on all the faces. This is the sliding 15 puzzle designed for 2 players. So you have to move those tiles so that each row and each column contain the numbers 1 through 5. Of course, this is already solved. There is an empty slot here that you can use to move, to slide tiles. So you can slide this 1 tile into that empty position, then maybe this 4 tile in there. This is, of course, already solved, but you start with a disorganized grid, and then by moving blocks into the empty slot and shifting them around, you have to solve this. And this is for 2 players. Basically, they race against each other to see who completes the puzzle first. Okay, so Sudoku puzzles are basically consist of putting numbers into squares or cells while honoring some constraints. Now, task scheduling problems are similar because they too, we have a set of tasks. In Sudoku, we have a set of numbers, 1 through 9. There are some processors that can execute tasks. And in Sudoku, we have cells that can hold numbers. And then we have to assign tasks to processors so as to meet certain constraints. Of course, in Sudoku, we have to place numbers in cells while honoring some constraints. Now, a task may fit only some processors. In other words, only some processors can execute a particular task. Tasks may have prerequisite tasks. In other words, some other task must be performed first before we can execute a particular task. We may have preemption, allowed or disallowed. Preemption means leaving a task in the middle and then coming back to finish it. When you read a book, for example, you can bookmark a page. You can, if something more urgent comes up, you bookmark the page you were reading, go do the more urgent thing, and then come back and resume your reading from the point that you bookmarked. So book reading can be preempted by a more urgent task. But there are some other kinds of tasks that cannot be preempted. We don't want to allow preemption. Tasks may have deadlines. Okay, they may have to be finished by a certain clock time. And those deadlines are given to us, and then we have to schedule them to make sure that the deadlines are met. And then we may seek the shortest schedule. In other words, to be able to finish all tasks in the shortest possible time. And in Sudoku, we have to use only numbers 1 through 9. Some numbers are already placed, so those are the constraints basically that are already given to us. Those numbers must go into those cells. We must have different numbers in each row. We must have different numbers in each column. We must have different numbers in each block. Okay, so you see that the two activities, the two things are very similar. Basically, we have options and we have constraints that we need to meet. And then we try to optimize something. For example, in Sudoku, you may try to finish it as soon as possible. Sometimes you time yourself, okay, to see whether you can finish an easy Sudoku puzzle in 3 minutes. Once you have enough practice, maybe you can do it in 2 minutes and so on. So now virtually all instances of the task scheduling problem are difficult, NP hard, just like Sudoku. So Sudoku has been theoretically proven to be NP hard. That's why it's an interesting puzzle. There are no shortcuts. You basically have to work hard in solving a Sudoku puzzle. Another set of problems that are similar to Sudoku are resource allocation problems. So we have a set of resources corresponding to numbers in Sudoku. There are locations where resources may be placed. So an example of resources may be police stations or fire stations. So we have a city and we want to place fire stations in this city. And there are only certain locations that are suitable for placing fire stations in terms of accessibility and so on. Now cells in Sudoku puzzle can hold numbers. We have to assign resources to locations to meet certain constraints. Place numbers in cells while honoring some constraints. A resource may fit only some locations. Resources must be easily accessible. Resource mobility may or may not be allowed. So some resources may be mobile. So for example, if you want to put police patrol cars in different locations, those are mobile. Once you place them at some location, you can move them to other locations. Whereas if you're placing police stations, those are not mobile. Resource cost may differ by location. It may cost different amounts of money to build a police station in various locations. For example, land prices are different. Construction prices are different in those locations. And we may seek the lowest cost assignment. Again, virtually all instances of the resource allocation problem are difficult or NP hard, just like Sudoku. So when problems are NP hard, it means solving them exactly typically requires a large amount of time. We sometimes resort to heuristic algorithms. Heuristics are algorithms that give us a solution that is not guaranteed to be optimal, but it's often not too far from optimal, depending on how good the heuristic. Or sometimes we use approximation algorithms. We approximately solve the problem. Again, the approximate solution will not be optimal, but it's close enough that we can live with the slight inefficiency in the solution. Okay, so let me give you an example of scheduling. We deal with scheduling every day, all of us. We have various activities. We have time slots for performing those activities. So some time slots may be already taken by classes or meetings that have already been scheduled. And then we schedule our other activities in the remaining time slot. And then we have constraints. We want to leave ourselves, a lunch break. We want to go to bed at a reasonable time. So those are our constraints in scheduling our daily activities. Here's another example of scheduling courses to be taken in different quarters. So these are, again, computer engineering required courses from some years ago. Some of these have changed, but doesn't matter. So what this chart indicates is that you have to take Math 3A or somehow be exempted from taking it before you can take Physics 1. You have to take Physics 1 before you take Physics 2. Okay, you have to take Math 3C before you take CS40. As I said, these may have changed over the last few years. Okay, so your task is to schedule these courses for various quarters of your studies at UCSB. And a simple, straightforward, assuming that every course is offered in every quarter, and that's iffy because in fact some courses are not offered in every quarter. But assuming that they are, then you basically proceed by layers. You say, okay, these courses in layer 1 that do not have any prerequisites, I can take in my first quarter. And the units are color coded here. Orange is 4 units, 4, 5, 8, 9. 9 units is basically doable in one quarter. So you can take all the courses in that layer in one quarter. Again, assuming that every course is offered in every quarter. So this will be fall quarter freshman year. Then winter quarter freshman year. Again, let's count the number of units. 4, 8, 12, 15, 16. Okay, that's manageable too. I'm ignoring, the general education requirements, language, and so on. I'm just focusing on scheduling these courses. Then these 3 in the third quarter. Again, that's 12 units. When I get to this quarter, that layered approach fails because I have 4, 8, 9, 12, 16, 20 units. That is too many units for one quarter. Then I can basically modify this diagram by moving, let's say, CS40 to a later quarter, and then modify the connections. Okay, so this is basically scheduling. Scheduling means choosing the courses for each quarter so that you're satisfying various constraints, like total number of units in one quarter is one constraint, and then prerequisite is another constraint. So CS40 must come at the later quarter than Math 3C and CS10 because those two are prerequisite. So these arrows should always go downwards. They can't go upward. There are sometimes co-requisites when the arrows can go sideways. But other than those co-requisites, the arrows should always go downward. Okay, so there's an example of a scheduling problem. Scheduling courses for different quarters of a student's studies at UCSB. Okay, now scheduling has a long history. In fact, in computer engineering courses, we talk about task scheduling on processors. So we do it in the context of computing with our processors that can execute tasks. But scheduling has a long history and was done way before computers even existed. The problem was known as job shop scheduling. Okay, so what is job shop scheduling? There is a machine shop with different machines where people use to build different things. So typically the machines are drills, lathes, various shaping machines that you can take a piece of metal or wood or some other material and shape it by shaving parts of it, cutting parts of it, drilling holes in it, and so on. And then you make different pieces for a car or some other mechanical device. Okay, this machine shop has a manager who schedules the activities of different workers in the machine shop and different machines. Okay, and the manager is motivated to use the machines and staff as efficiently as possible so that their time is not wasted. The machines, some of them can be pretty expensive and therefore they have to be used quite efficiently. So here I've shown an example where there are 4 jobs that need to be done. Job A, job B, job C, job D. And then each job has tasks. So for example, job A has 2 tasks, A1 and A2. Job B has 3 tasks, B1, B2, and B3. Job C is just a single task. And these have to be done in order. So job B, in order to perform job B, you have to perform task B1 first, then B2, then B3. This may be cutting the piece of metal to size, for example, job B1. This may be cutting a corner of it because the shape is irregular. And 3 may be drilling a hole in it. So these have to be done in the order specified by those tasks. Now each task requires the use of a machine. So A1 requires us to use machine M1, A2 requires us to use machine M2, and so on. So each task requires the use of one of the 3 machines, and we have 3 machines color-coded. The blue M1 machine, the green M2 machine, the orange M3 machine. And then performing that task requires a certain amount of time, and the unit of time is not important. Let's say we assign time in increments of 5 minutes. So 2 units of time means 10 minutes. 6 units means 30 minutes. So 2 units and 6 units of time. And then it requires a certain number of staff to do that task together. Okay, so it's a fairly complicated. And the manager basically early in the morning may come into the machine shop and try to figure out what's the best way to assign these jobs and their tasks to staff members and to machines. So let's say we have 8 staff members. So on the vertical axis, you see staff member 1, 2, 3. So that's one resource that we have. And the other resource is time, up to 16 units of time shown in this chart. Okay, so each task, scheduling of each task represents putting a rectangle on this grid. So task A1, this one, requires the use of machine M1, which is blue coded. So I put a blue rectangle there. It needs 2 time units. So the horizontal dimension of this rectangle is 2. And it needs 3 staff members, 3. Okay. Now anything else that needs to use machine 1, like this one or this one, cannot be done during those 2 time units, because machine 1 is occupied during those 2 time units with this particular task. So those are constraints. Okay, a machine can be used on one task at any given time. So D1, which also uses machine 1, can be scheduled here. It goes from time unit 2 to time unit 7, and it uses 4 staff members. Notice that these 2 boxes do not overlap, meaning machine 1 is used here, and then immediately afterwards it's used to do this task. I can't stack boxes on top of another for the same machine. I can't put TD1 up here stacked with TA1 because they both use the same machine. Okay, so I can continue. You see now why this is a puzzle-like activity. I can cut those rectangles according to the characteristics of the various tasks, how much time they need, how many staff. So a 2 by 3 blue rectangle, a 6 by 2 orange rectangle, a 5 by 2 green rectangle, machine 2, and so on. And then I have to sort of put those next to each other until all of them have been placed. And I would like to do that optimally. So what do I mean by optimally? Well, if time is the most important concern, then optimally means to finish everything as soon as possible. In this example, 13 time units are needed to finish this. And in the worst case, I need 8 people. Now, if I already have 8 people full-time working in the shop, then it doesn't make sense, saving. But maybe I can move some of these boxes around so that I can use fewer people, or maybe less time. Okay, if these employees are paid by the hour so that they're not paid when they're not doing work, if I can limit the number of staff to 7, if I can fit all of these puzzle pieces inside a box of height 7, then I save the salary of 1 staff member. If I can fit it in a box of width 13, then I can save 1 unit of time, finish things faster. Okay, so a natural question, is this the best I can do? So the manager basically constructs the schedule and then worries, can I do better? Of course, the manager does not have an infinite amount of time to try many different possibilities. This is an NP hard problem, and therefore there's no shortcut. You have to basically try many different possibilities, exponentially many possibilities, to find the best. But the manager perhaps comes in half an hour before the other employees and has only half an hour to find a schedule that is reasonably good, and therefore within that time constraints, he or she constructs the best schedule that can be obtained in that time unit. Here is another schedule. Again, it's easy to verify that this schedule satisfies all the constraints. Notice that the blue boxes do not overlap. They're not stacked. The orange boxes are not stacked. The green boxes are not stacked. Okay? Therefore, all the constraints about one machine being used for one thing at a time are satisfied. This one requires 16 time units, but only 6 employees, 6 staff members. So the question is this better than that one? Okay, well, the answer is it depends. How do you define better? One way to define better is the product of the number of employees by the number of time units. So 6 times 16 is 96. Again, if we pay employees by the hour, then 6 times 96 is basically the total cost, staff cost for this. This one is 8 times 13. 8 times 13 is 104. Okay, so in that sense, the second schedule is better, although still there's no guarantee that it's the best possible. Okay, once we have a feasible schedule, something that is reasonably good like the one you see here, we can sometimes fine-tune it by shifting those tiles or boxes around, seeing if we can do better. So for example, here's an idea. Should I switch the locations of TB2 and TD1? Both of them use machine 1, but I can do them in a different order, like this. TB2 first, TD1 next. Oh, remember that the constraint that TB1, TB2, TB3 must occur in that sequence in time. Okay, task 1 of job B, task 2 of job B, task 3 must appear in that order in time. You can't switch them around. So TB1, TB2, TD2. And now with this change of TB2 and TD1, I'll try to put the other boxes. And sure enough, I was able to shave 1 time unit from the completion time. And therefore, that switch of the 2 tasks, D2 and D1, was a wise one because it led to a better schedule. Okay? Again, just because this schedule is better than the previous one doesn't mean that it's optimal. I may be able to do even better than this, but I usually have a finite amount of time to figure out what to do. And once the solution is reasonable, then I just basically let it go forward and don't obsess too much about making it even better. Okay, here is another example of scheduling. This is truck scheduling. This is something that is done daily throughout the country by companies that own trucks, shipping companies basically, and they have to schedule their trucks in the most efficient possible way. So here I give you a toy example where I have just 5 trucks. So this company has 5 trucks, and those trucks are currently in these locations: Los Angeles, San Francisco, Chicago, New York City, and Orlando. There are 5 trucks. They're there because maybe the last thing they carried took them to those cities. And they're now waiting there to get new assignments, new schedules to transfer things between cities. Okay, so let's say I have these job orders. So the trucking company has the trucks in those cities, and these blue arrows indicate orders that have come in, customers who want to ship things. And each shipment is characterized by how much of the space. Imagine all of these trucks are semi-trucks of the same capacity. Okay, so I'm simplifying things because trucks may be different sizes. So let's say they're the same capacity and the shipments are formulated in terms of what percentage of the truck capacity the shipment will need. So this shipment from San Francisco to Seattle takes 35% of the truck's space, meaning that 65% is empty, and I can combine this with another shipment if there is any shipment that is headed in the same way. The shipment from Portland to Chicago takes 50% of the truck, and so on. From Los Angeles to New York City, there's a shipment that takes 75%. So that one cannot be combined with any of those other shipments except with this one possibly. 75 plus 20 is 95, okay? So now the truck, nowadays, the truck companies have programs, software that do the scheduling. But imagine we wanted to do this scheduling by hand and assign these shipments to the 5 trucks. It seems that the truck in Orlando is basically, it's unlikely that we can make use of that particular truck. So let's focus on, there's a truck in San Francisco and there's a shipment from San Francisco to Seattle. So let's basically load that shipment and send that truck. So that truck basically is less than half full as it moves from San Francisco to Seattle, but there's no other option because we can't combine that shipment with anything else. So that shipment is taken care of. Then we may have that truck come back from Seattle to Portland and then load up the shipment that goes to Chicago. That takes up only 50% of the truck space. So rather than send the truck directly from Portland to Chicago, we may decide to send it to Boise and have it pick up that 40% shipment from Boise to Dallas. So the truck is now 90% full, 50% with this shipment and 40 with this. And then it drops off that 40% in Dallas and is left with 50%. So it can load up the 20% shipment from Dallas to New York City and head to Chicago to drop off that 50% shipment, and then eventually from Chicago to New York City. Okay, so you see that this is pretty complicated, trying to make best use of the trucks and the drivers of the trucks, and basically we want to make each truck as full as possible so that when we pay for gas, truck depreciation, driver salary, we transport as much as possible on that truck. Okay, so it's a pretty complicated solution. Now imagine instead of 5 trucks, we had hundreds. A large trucking company may have hundreds of trucks. And then instead of just a few shipping orders that you see here, we have many thousands of shipping orders. So you can imagine how difficult it is to find an optimal schedule or near optimal schedule for the shipping. Okay, of course, in computer engineering, we are primarily interested in scheduling tasks on multiprocessors. And tasks are represented as graphs shown on the right side of the slide, where each of those circles is basically a task. Now I'm making things extremely simple so that I can discuss solutions without having to teach you an entire course in scheduling theory. So these tasks are unit time tasks. Each of them takes 1 time unit to execute. And then all the processors are identical, and any task can be scheduled on any processor. Okay, similar to that trucking simplified trucking algorithm. We assume all the trucks are the same size, and therefore it doesn't matter which truck is used for a particular shipment. Okay, so scheduling algorithms are difficult. Finding the optimal schedule, even for these unit time tasks, if we have more than 2 processors, the problem is NP hard. With 2 processors, the special case of just 2 processors, we have efficient algorithms for schedule. But as soon as I have 3 processors, or if my tasks are not unit time tasks, then the problem becomes messy. So here is a heuristic known as list scheduling. So remember, I said heuristic is something that does a decent job of solving the problem. It doesn't guarantee optimality, but usually, experience shows that it does a good job, and therefore we evaluate heuristics by running them on various actual problems and then rank them. Say this heuristic did better than the other one, and therefore we use that for our particular application. So this heuristic goes like this. First, determine the depth of the graph. The depth is basically the length of the critical path from the starting point to the end point. For this particular graph, the critical path has 1, 2, 3, 4, 5, 6, 7, 8 nodes. And these arrows are prerequisites. In other words, no matter how much resources I have, it's impossible to execute this task graph in fewer than 8 time units. Okay, I need 1 time unit to execute this one. Another one, they have to be done in order. 2 time units, 3 time units, 4 time units, 5 time units, 6 time units, 7 time units, 8 time units. Okay, so I take that's called T infinity, or the depth of the graph. That's basically how much time I need if I have an infinite number of processors, no limitation in the number of processors. I would still need 8 time units. So T infinity is 8. Take T infinity as the goal for the running time TP. TP is the running time with P processors. Of course, there's no guarantee that with, say, 2 processors or 3 processors, I can achieve this running time. But initially, I take that as my goal. Okay, I try to do that. Determine the latest possible start times for the task. Okay, if I need to execute this task graph in 8 time units, then this has to be done at time unit 8. Therefore, I have to start it at time unit 8. So the latest possible start time for that is time unit 8. Now, the tasks that are prerequisites for this one must start by time unit 7, because if I execute these by time unit 7, then this one can be completed in time unit 8. All the prerequisites of these tasks, time unit 6, and I use these numbers as priorities. So I say this task has the highest priority, priority 1. In other words, if I don't execute this task right away, there is absolutely no chance that I can complete this task graph in 8 time units. Okay, this has the highest priority. This has the second highest priority. This has the third highest priority. This has the fourth highest priority. This has the fifth highest priority. Now these 4 collectively have the 6th highest priority. So I need a secondary criterion to break the tie and say, okay, which one is higher priority than the other one? And there are various decision mechanisms used for that. Let's say that I basically use some arbitrary scheme and assign priorities as shown in the red numbers. So this node, this task is priority 1, priority 2. The red numbers are priority 3, 4, 5. Now among these 4, I assign priority 6 to this one, 7, 8, and 9. Okay, I've used some criterion that I'm not, discussing here, whatever that might be. And then these 3 are in the same level, so I continue, let's say, assign priority 10 to this one, 11 to this one, 12 to this one. I could have done it differently. And then priority 13 to this one. Okay, once I have the priorities, I list the task in order of the priorities. In this particular example, the priority number and the task number happens to be almost the same. There is just a difference here. So task 1 has priority 1, 2 priority 2, priority 3, priority 4, priority 5, 6 has priority 5, and 5 has priority 6. Okay? And then I execute the tasks in order of their priorities whenever they are executable. So at the very beginning, only task 1 is executable because none of the others have their prerequisites met. So that's indicated by putting an asterisk next to the number. So I execute 1, then 2, then 3. So on a single processor, I need 13 time units to execute all 13 tasks, which is sort of obvious. I have 13 things to do. Each of them takes a unit time, and therefore I spend 13 time. If I have 2 processors that can basically collaborate, this might be a schedule. Again, 1 is scheduled first, and at the time I execute 1, I cannot do anything else because no other task is ready. Therefore, processor 2 goes to waste here. Then 2, then 3, so there's a sequential dependency chain, 1, 2, 3, where nothing else can be done. Therefore, one processor executes that. The other processor is idle. But once I get to this point, tasks 4 and 5 have their prerequisites met, and therefore I can schedule them together. Okay, so 4 at this point has the highest priority. This one has the highest priority, but it's not after this one, but it's not ready to be executed. So I go to this one. And now with 2 processors, I can execute this in 9 time units instead of 13. I couldn't quite double the speed because of these waste of processor times. So ideally, if I use 2 processors, I should be able to do things twice as fast. But because of these dependencies, I can't do it. Then I go to 3 processors. I can achieve that minimum possible time, 8 t infinity. And therefore, that's a sign that if I increase the number of processors beyond 3, I cannot reduce the running time any further. So 3 processors are the maximum that can be gainfully employed to speed up the process of executing these tasks. Okay, here are 2 related similar problems. The knapsack problem and the offline game of Tetris. The standard Tetris is an online game, meaning that the pieces basically start falling from above, and then you have a limited time to decide what to do with each piece before it hits the bottom and basically becomes fixed in its position, and you can't do anything about it at that point. The offline game basically gives you that bin into which the pieces of Tetris must go. It's basically a rectangular bin. And then you have a string of Tetris pieces given to you ahead of time. So you know the first piece, for example, is one of these, the second piece is one of these, the third one is one of these. So you have the entire set of pieces that will be coming down, and you have an unlimited amount of time to decide what to do with the pieces. It's not an online game. Nevertheless, it's still pretty difficult because each of these pieces can be rotated and put at the bottom of the bin, and then you have to decide what's the best decision for each piece. And if you have played Tetris, you know that if a row is completed at the bottom, that row disappears, and therefore you get more chances to accommodate additional pieces. Okay, so what is the knapsack problem? We have a storage capacity W and n files of sizes W sub I and values V sub I. So you have, let's say, a disk drive of a particular size, and you have a whole bunch of files. Each of them has a size and a value or worth to you. And then you want to put those files, as many of those files as you can fit, onto the disk or into the storage in order to maximize the value. Okay, so if you have a file that is small and of high value, you definitely want to put that in. If you have a large file that also has a large value, then it's not certain whether you want to put it in. So it's a very difficult decision. It's a difficult problem to solve. It's NP hard. Okay, and in the case of offline Tetris, you try to find the optimal play to maximize the number of pieces used. In the case of the knapsack problem, files cannot be broken into pieces. This is sort of similar to non-preemptive scheduling, because the problem becomes simpler if you can cut a file into two pieces and then try to fit the pieces in. The naive solution requires for you to examine all to the n possible subsets of files. Obviously, that will be very slow. There's a dynamic programming solution to this problem, and there are various heuristic aids. There are also approximate solutions that basically come pretty close, say 90% of optimal. So if the optimal, for example, is to accommodate files of total value 1000 into the space, 90% of 1000 is 900. So if the heuristic allows you to accommodate the value of 900, that's judged to be a good heuristic. Also in Tetris, there are exponentially many choices because for each piece you have various rotations. And then if you consider 10 pieces in a row, each of them having several rotations, let's say 3 rotations, then you have 3 to the power 10 possible choices for 10 pieces. And if you have hundreds of pieces, then the number of choices will be even larger. Okay, so this is basically all I wanted to say about scheduling. Remember, this was lecture 7, and it's scheduled for May 11th. So in your attendance report, please mention that this is lecture 7, 05/11, the scheduled date, and submit your reports by Wednesday, May 13th, 6:30 p.m. Thank you, and see you in the next lecture.